This is a continuation of our continuation of types of chemical reactions. So we had synthesis as the first reaction type and decomposition as the second reaction type. And now we've still got the second reaction type, which is decomposition, but these are special cases. They're common decomposition reactions. It's up to you if you're going to learn them or not, but here they are, and they're fairly common. There's going to be 5 of them, and 4 of them are okay, and then one of them, actually, 3.5 of them are okay, and then one's not so intuitive, and one's even less intuitive. So we're going to jump right in. We've got a bunch of examples to do. Our first type of special decomposition, I'll just declare it's A, just so we can keep our things separate, is the decomposition of metal carbonates. All right. Now, the first thing I want to mention is in order to have decomposition of metal carbonates, you have to have a metal carbonate, right? And if you forgot, carbonate is the polyatomic ion, CO3 2-. Our general form then is going to be, you have some metal carbonate, you're going to heat it up, and you're going to get a metal oxide. And a little life advice, which is CO2. Very often when you decompose a carbonate, you get carbon dioxide, and that's going to be a theme in our last type of special decomposition. But this is how every single one of them looks. You got a metal carbonate, that's something left of the jagged line on the periodic table. Attach the carbonate, you decompose and you get a metal oxide and carbon dioxide. And we looked at that in a synthesis scenario. If you remember back to the synthesis video, at the end I did some reactions that were the reverse of some special decomposition reactions. Well, guess what? We're there now. We just got to that point. So we're going to look at 3 very quick examples, because there's just a bunch we have to do. So we'll start with maybe silver carbonate, and we'll heat that up. All right. In fact, let me do this just because I think it'll look funnier. We've got then maybe magnesium carbonate, and then we'll heat that up. And how about iron 3 carbonate? And guess what we're going to do? Yeah, we're going to heat that up. The reason I want to throw all those out there at once is so you can see how this general form works. Metal, 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 carbonate, 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 something, 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 and CO2, and CO2, and CO2, right? So all we're doing is changing this step based on what metal we have. And that metal is going to be an oxide. It's going to bond with oxygen. And the way we're going to get that formula is crisscross and reduce. So in this case, I've got silver with oxygen, right? In this case, I've got magnesium with oxygen. And in this case, I've got iron, and it's the iron 3, if you're wondering, with oxygen, all right? Don't get too excited because we haven't actually written the formulas for these. We need to crisscross and reduce, right? So let's see what we can do here. Silver's a 1+, and oxygen's a 2-, so I can put a 2 there. And that is my formula for silver oxide. When you get to the product side and you need a formula, this is for any of our reaction types, crisscross and reduce, all right? That's how you're going to come up with it. Don't look at the other side, whatever this means, right? Look at the crisscrossing and reducing. In this case, it's a 2+ and a 2-. And so when we do crisscross, we'd have a 2 and a 2, but it reduces, right? When we're talking about ionic compounds, we're talking about formula units, not molecules, and formula units are always the reduced form. All right, so we got Mg2O2 becomes MgO, that's fine. This is iron 3, right? And oxygen's a 2-, so we'll need a 2 there and a 3 there. And again, the whole point of crisscrossing and reducing is to get an electrically neutral species, if you like that terminology. I've got 2 times 3 is 6 pluses, 3 times 2 is 6 minuses, 6 minuses and 6 pluses end up 0. All right, all these are going to have to be balanced, and we'll see if I can do that in as little space as possible. Maybe I can even like triple fake it, and we'll set it up like this. Reactants and products. And we'll split them with maybe a black line for our species, all right? And let's see what we got here. Silver carbon oxygen, silver carbon, oxygen. This one's magnesium, carbon, oxygen. And this one's iron, carbon, oxygen. You noticing a theme? You've got 2, 1, 3, and this one you've got 1, 1, 3, and in this one you've got 2, 3, 9. All right, so it's worth noting there, 2 of those irons, 3 of those carbons, and 9 of those oxygens. All right, I was negligent. I should have handled these one at a time, but we may as well continue with this strategy. On this side, I've got 2 silvers. Good. I've got 3 oxygens. That seems promising, and 1 carbon. So that's balanced. Awesome. All right. On this one, I've got magnesium, 1 of those, oxygen, 1, 2, 3 of those, and carbon, 1 of those. Spectacular. And now we'll see if we can get lucky a third time, which obviously we won't. Irons, we have 2 of those. Carbons, we have 1 of those. And oxygens, we have 3, and 2 is 5. All right, and we better double check. 3 there, 2 there is 5. And we got our carbons and our oxygens. In case you didn't notice, it's not balanced. We'll try, like, my general strategy, when in doubt, work top to bottom. So we'll say I've got 2, that looks good, 3 does not, so let's take care of that. We'll get our 3 carbons on the product side, and that changes our oxygens. And I'm going to warn you, this is a super, super common trap people fall into. I get so excited about the 3 I put here making 6 oxygens that I forget about the 3 oxygens over there. And it'll happen at some point to you, so just forewarned. 3 times 2 is 6, plus another 3 is 9. And best case scenario is it ended up balanced, right? So all of these exactly the same. We've got this decomposition of a metal carbonate, and we have our metal turning into a metal oxide, and then everything is CO2, right? All right, so that's our first type of decomposition reaction. Our second type is going to be the decomposition of metal hydroxides, all right? So the decomposition of metal hydroxides, and guess what you need for that? That's right, metal and hydroxide. Okay, our general form has to be very similar. We're going to take a metal hydroxide. We're going to heat it up, and we're going to get a metal oxide again. But this time, since we have that hydroxide, water happens to be a pretty stable species, so we're going to get water, all right? And I'll put that in as a gas. In the big picture, it's not that big a deal for qualitative purposes. If you're doing thermodynamic calculations, it might be a different story. But since you're heating it, H2O gas, good place to start. All right? Let's get our examples here. Again, I've got 3 of this. And if you're wondering why I chose the examples the way I did, I want a 1 plus, a 2 plus, and a 3 plus generally for these examples. And they may or may not be done in that order. So let's get our 3 examples in this case. First one, let's toss out KOH, which is actually the trickier one of the bunch, and maybe copper 2 hydroxide. And we'll go with aluminum hydroxide. If you forgot, the little triangle there means heating things, right? That was covered in our chemical equations video. But we're heating that stuff up. One of our products has to be water, so I'm just going to go ahead and put that in there right away. H2O, H2O, and how about H2O? So you'll notice the symmetry of how these decomposition reactions do the same thing. What's here changes based on the metal you add here and whatever formula it makes with oxygen. So that's the exact same scenario. So we're going to have a metal oxide. Well, I've got potassium. That's my metal. I've got copper. That's my metal. And I've got aluminum. That's my metal. It's got to be with oxygen. It's got to be with oxygen. And it has to be with oxygen. All right. We'll get our oxidation states here and see where we can go from there. Potassium's a 1 plus. Oxygen's a 2 minus. 2 plus in this case. And if you're wondering how I guessed that, it's because I just put that 2 up there. 2 minus. Aluminum, 3 plus. It's group 13 of the periodic table. Oxygen's still 2 minus. You'll notice a lot of these examples, and a lot of the examples that I do involve oxygen. Well, it's not surprising because it's the most abundant element on Earth, so it's in a bunch of compounds, right? And oxides tend to be lower energy states in many cases. All right, so I'm going to put a 2 there. I'm going to bring a 2 and a 2 down, and they're going to reduce as a 1 and a 1. I'm going to put the 3 there and the 2 there. All right. I did this in the synthesis video just so people wouldn't get overwhelmed. Like, I'll cross those out. Those never happened. All right. They're not part of the answer. We never saw them. All right. So now they're gone. We need to balance these, and we're going to set it up exactly the same way we set up the previous ones. We've got our reactants and products. And I'll split that up, and we can make it happen. My spacing is terrible this time, but I can make it happen, right? All right, first one, we've got potassium, oxygen, hydrogen. Potassium, oxygen, hydrogen. And let's do this in a more legit fashion. 1, 1, 1. And on this side, 2 potassiums, 1 oxygen here, and 1 oxygen here is 2 oxygens and 2 hydrogens. So 2, 2, 2. All right, 2 there, 1, 2 oxygens, 2 hydrogens. We put a 2 there, 2, 2, 2, and we're all set. All right. Moving right along here, we've got our copper, oxygen, and hydrogen. Copper, oxygen, hydrogen. Copper, we've got 1 of those, 2 of those, 2 of those. Product side, 1 copper again, 1, 2 oxygens, and 1, 2 hydrogens. That's convenient. That one's already balanced. And then we've got our aluminum hydroxide. We've got aluminum, oxygen, hydrogen. 1, 3, 3. And then on the other side, I have 2 aluminums all of a sudden, and 4 oxygens with 2 hydrogens. All right. Again, when I don't have a strategy, my strategy is just to work my way top to bottom. So maybe I'll try and fix those aluminums first. Double what's on the reactant side. Gives me 2 aluminums. But now I have 2 times 3 times 1 is 6 oxygens, and 2 times 1 times 3, which is 6 hydrogens. It's not balanced. But maybe I'll work my way down here. Like, oxygen looks a little scary because it's in 2 places. So that's another hint I'll give in terms of balancing. If you've got something that appears in more than one place, save it for later if you can. So we've got the hydrogens. Let's try and take care of those. We'll put a 3 to get 6. And the good news is 3 here and 3 here is 6. And again, very, very dangerous pitfall is forgetting that these oxygens occur in 2 places. I get excited. I'm like, I put a 3 there. Now I have 3 oxygens. And I forget about the other 3. So watch out for that. All right? All right. Next up, decomposition of metal chlorates. I think you've noticed the pattern, which is the general form is going to be, in this case, a metal chlorate, and I'm going to heat it up. All right, so my general form, I'm going to have a metal chlorate. I'm going to heat it up, and I'm going to get something. All right, and this is one that you kind of just have to remember if you're going to learn these special decomposition reactions. This is one you're just going to have to remember. In this case, it's a metal chloride and oxygen gas. And this is a super common demo when you do this with potassium chlorate. I guess I'll mention that as we look at that specific example. We're going to do 3 examples again for these, and we'll fill our space well. All right, first one, KClO3. Then let's do maybe nickel 2 chlorate and iron 3 chlorate. All right, so looking at these, we just make it an assembly line, right? Same deal. And the reason I want to do these back to back like this, and the reason I want to just do them all at once, is because they're all the same. You just have to change a couple little things. The process and the breakdown is the same. So I'm going to have oxygen, oxygen, and oxygen. All right. And oxygen happens to be a really good oxidizer. And that's what's needed for combustion. So it's very common, I do the demo, in fact, and a lot of people do. You toss some solid potassium chlorate into a test tube, and you heat it up, and it decomposes into oxygen gas. And in this case, our metal chloride is potassium chloride, K, which is a 1+, and Cl, which is a 1-. So you get molten potassium chloride and oxygen gas. There's a bunch of energy in there, so you throw a gummy bear in there and it becomes a flamethrower for like 20 seconds. It's one of the neatest demos you can do, like in my opinion, because it's this flamethrower out of a test tube just from like throwing a gummy bear in there. It's shocking how much energy is contained in those things, or in like any candies that we have. All right, let's complete these other ones, and we'll get our charges balanced, and we'll get things moving here. This is nickel 2. Again, it's a transition metal, so I'm just going to fake my knowledge of what these charges are going to be by uncrisscrossing them, right? So I've got nickel in this case, and it's going to be with chlorine, and I've got iron in this case, and it's going to be with chlorine, because those are our metal chlorides. Let's add in 1-, 1+, 1-, 2+, right? That's where I'm pulling that from. And then 3+ and 1-. We just crisscross and reduce. KCl looks good, NiCl2 and FeCl3. All right, and I'll go back and do what I did moments ago, which is make the evidence of our crisscrossing disappear. It's not actually part of the answer. This just leaves balancing, so let's make that happen, and then we can get to our last two reaction types and see how those go. We'll set up our table, reactants and products, and we'll divide that up a little bit. Let's see if we can zip through these. We have K, Cl, and oxygen. We have nickel, Cl, and oxygen. And we have iron, Cl, and oxygen. Hopefully you're noticing that theme as we go. This side 1, 1, 3. This side 1, 2, 6. And do take note, this 2 modifies the 3, and the 2 also modifies the 1 chlorine that we have there. All right. Similarly, this 3 is going to modify the chlorine and the oxygen. So we'll have 3 chlorines and 9 oxygens, right? And we have 1 iron. Product side, we've got 1 potassium, 1 chlorine, and 2 oxygens. My hopes were so high as we got closer there. We've got 1 nickel and 2 chlorines and 2 oxygens. That's not helping us. And we've got on the iron one, 1 iron, 3 chlorines, and 2 oxygens. There's actually some mildly interesting balancing that's going to happen here, but let's take care of the other ones first. We have this 3 and 2 scenario, so 6 is going to be the solution. 3 there, excuse me, 6, and a 2 there is going to give us 6 oxygens. In the process, though, we screwed up the potassiums and the chlorines. That 2 potassiums, 2 chlorines, 6 oxygens. So we're going to fix that by putting a 2 right there. All right. Looking at this one here, nickel looks good, chlorine looks good. I can fix the oxygens by putting a 3 right there. That's easy enough. And now something exciting happens, right? This is a situation that comes up very often in combustion reactions, hydrocarbon combustion reactions, and a few other types. And what we have to do is deal with a situation where we have forced odds on one side and forced evens on one side with a bunch of stuff. And you'll see here. Iron looks great, chlorine looks great, oxygen does not, okay? And I need to get something over here that's going to turn a 2 into a 9. And like when I ask this question in class, kids stumble over it because like I need the dumbest answer possible. What's the dumbest answer for a mixed fraction times 2 that is 9? And the answer is 9/2, all right? This is a brand new marker. 9/2. All right, so if I do that, take a look now. 9/2 times 2 gives me 9, and it's totally balanced, right? We do have to fix that, though. We're not allowed to leave it that way. There are situations in thermochemistry for like enthalpies of formation and things like that where you will use fractional coefficients. In general balancing, though, we don't use fractional coefficients, and the solution to this is to just multiply the whole thing by 2. There's plenty of ways to do it, but it's a super slick algebra cheat to just use the fraction and fix it. What's going to make 9/2 go away? I'm going to multiply the whole reaction by 2. So I'll have 2 of those, and now I have 9 of those, and let's check. 2 irons, 2 irons. Good. 6 chlorines, 6 chlorines. I've got 3 times 3 is 9 times 2 is 18 on the reactant side for our oxygens, and then 18 on the product side for our oxygens, and it works. All right? So interesting balancing situation there, kind of a neat one to look at, and we'll see it again when we do combustion reactions. All right? Now the less exciting stuff starts, and by less exciting stuff, I mean less intuitive stuff. So we've got our special decomposition A, B, and C, and let's go on to a D option, all right? And that is the decomposition of oxyacids. And I'm going to try and budget the space a little differently here, because there's more words that I want to include. If we're going to use this term oxyacid, we're going to have to establish what is an oxyacid. And an oxyacid happens to be an acid containing an oxyanion. All right? And that probably doesn't help most people with the definition. So let's expand on that a bit. What is an oxyanion? Well, an oxyanion is a polyatomic anion containing oxygen, right? So polyatomic anion containing oxygen. Okay? And so an oxyacid is an acid with a polyatomic anion containing oxygen. And like if you want to super streamline that whole thing, so an oxyacid is some hydrogen with an oxyanion. And I think it's worth taking a moment to look at how our oxyanions combine with hydrogens to make oxyacids. So if we look at some common oxyanions, examples, you could have something like nitrate or phosphate or sulfate, and maybe even hydroxide, right? And then I can attach H's those, right? H's to them, and we'll get our oxyacid. So the corresponding oxyacids in these cases are HNO3, nitric acid, right? Hydrogen's a 1+, I needed 1 to balance that charge out, right? H3PO4, phosphoric acid, I needed 3 hydrogens to make that happen. H2SO4, sulfuric acid, I needed 2 H's, and then HOH, right, which is better known as water, which is an acid. Yes, and it also happens to be a base. And we call that amphoteric. And we'll learn more about that once we get into acids and bases. All right? Just fix my screen a little bit here. And we can dive into our decomposition of oxyacids. I think that, well, let's write the general form, and then I'll tell you the words. And that is, our general form is that you're going to have some oxyacid, and we're going to heat it up. And when we heat it up, we're going to get water. And I'm going to declare that it's water gas since we're heating it, and the rest. Okay? I think it's one of the easiest and simultaneously most unsettling decomposition reactions or general forms. Water and the rest. And we'll take a look at that right now with our blue marker. I've got 3 of these written out, so we'll do a similar setup here. Maybe we'll start with H2SO4, and we'll heat it up. Maybe HNO3, heat that up. And how about H3PO4, heat that up, right? And one of our products, in all 3 cases, is going to be water. All right? Then we have to have whatever's left. And this, I think, is the easiest one to see. All right? H2SO4, if I take H2O out of it, I have 2 H's gone, 1 O gone, SO3. I have SO3 remaining. And we looked at this in reverse as the synthesis reaction on the first reaction types, and now we're looking at it as a decomposition reaction, a special decomposition reaction. We'll go ahead and balance that in a bit, but I do want to glance at these other two because they're not as obvious. In fact, like when I do it, I often have to draw a picture because I'm not smart enough to keep track of stuff. So as we look at it, my other product has to be what's left. All right? And here's the problem. I only have 1 H right there, and I need 2 H's right there. So the first thing you have to do is start off by cheating a little bit. And in this case, I need 2 H's, so I'm going to start off by declaring I have 2 H's present, all right? And then I have 2 H's, 2 N's, and 6 O's, and I'm losing 2 of the H's and 1 of the O's. So what is left? In fact, like I'm going to show this over here because literally this is how dumb I am, but like H, N, O, 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 H, N, O, O, O. That's not at all representative of the structure, but I'm just counting pieces, right? I've got 2 H, N, O, 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 all right? And that's not the structure. That's not what it looks like, so don't get all upset about that. Let's take a look here. I need to make H2O. That's 2 H's and 1 of the O's. And what do I have left? N2O5. So the rest is N2O5. And that one ends up being balanced at that point as well. Get some color crises there. Some of these new markers aren't working. And let's look at the H3PO4. It's a situation like this one broke down H2, H2. This one we're going to have to do a little balancing on most likely. And this is, I would say, the least legit of the examples, but we'll just declare it's fine. We have 2 H's gone and 1 O gone, so we'll have HPO3. So I would have had H3PO4, and now I have HPO3. Whether or not that's true, that's what it says right there. And all 3 of these happen to be balanced as written because, well, with a 2 there, that's the nature of the game. But we'll play along. Spectacular space budgeting on my part. We've got hydrogen, sulfur, oxygen, hydrogen, nitrogen, oxygen, and hydrogen, phosphorus, oxygen. On this one, hydrogen's 2, 1, 4, and look at that on the product side, 2, 1, 4. 2, 2, 6, because we had to put that 2 in there so we'd have enough H's for H2O, 2, 2, 6. And then H3PO4, I've got 3 H's, 1 P, and 4 oxygens, and then I have 1 H, 1 P, and, sorry, I have 1, 2, 3 H's, 1 P, and 4 oxygens. So those are balanced. Hooray. And this brings us to our last, if not least liked, reaction type. Actually, this is my favorite of the bunch because it's kind of neat. The problem is it doesn't look like anything else. It doesn't look like decomposition, but it is. And it's the decomposition of a metal carbonate using an acid. All right, so if I just stopped right there, it says decomposition of metal carbonate, and look over here, decomposition of metal carbonate, right? But the key here is this is using an acid. All right, and we'll have to determine or define some terms here, but let's get our general form up there, and then we can start our downward spiral. Guess what we're going to start with? Metal carbonate. Oops, general form. We're going to have a metal carbonate, and we're going to not heat it for once. We're going to add in some acid. And what we get is something. And if you remember, when a carbonate decomposes, very, 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 very often it makes carbon dioxide. So I'm going to have CO2 as a product, and I'm also going to have H2 H2O as a product, which means something is there. And that something is a word you've heard before, but you may not remember it, and you may not remember it in the appropriate context. And that word is, it is a salt. All right. And table salt, NaCl, is an example of a salt, but there's many other examples, right? Like KCl. If you have someone who has high blood pressure, they might go to the grocery store and buy a product called not salt, right? Which is potassium chloride, because maybe the high blood pressure limits their sodium intake. All right, so a salt. And we're going to make up a super cheap definition of a salt. It's, and I'll make a slight adjustment because I know some people are super picky, but I'm going to say it's a metal cation with the anion from an acid. And now I'm going to put this word metal in parentheses, all right? Technically, you just have to have some cation with the anion from an acid, and that cation's not hydrogen. The majority of the time, that's going to be a metal cation. Ammonium is a common example of some cation, a polyatomic cation, but whatever, right? Something attached to the other part of an acid. And we're going to make up a super cheap definition of an acid as well while we're at it. And I'm just going to declare, like I did up here, that our oxyacid was hydrogen with an oxyanion. I'm going to declare right here that an acid is hydrogen with any old anion. All right? Not an oxyanion, but any old anion at all. All right, so we've got a few vocabulary terms worked in there. Let's take a look at a few decomposition reactions, and then we can throw in the towel. All right, we're going to do 4 of these. And we'll break down, again, in previous examples, I tried to break it down in terms of charges, and so we'll go through a few different charge options, and then a special one in the end. Ni2CO3, nickel 1 carbonate, zinc carbonate, ZnCO3, iron 3 carbonate, and a special one. Okay, each of these needs to be reacting with an acid, and so let's choose an appropriate acid here. How about HCl? That looks pretty simple. HNO3, hydrochloric acid, nitric acid, sulfuric acid. And how about acetic acid? CH3COOH. All right, or you might see that as C2H3O2H. All right. And it's a discussion for structures or anything else, but like, why do people write it as CH3COOH? And the answer is, it tells you about the structure. And I'm like, limited in space here, but CH3COOH literally says I've got a carbon with 1, 2, 3 hydrogens on it. And that's attached to a carbon that has 2 oxygens and a hydrogen. So I've got this. And it's an acid. It has the acetate polyatomic anion with a hydrogen attached, right? And so if you write C2H3O2H, this is technically correct. This is the acetate polyatomic ion, but it's other things. There are structural isomers, things that have the same formula and a different structure, but this tells us acetic acid, right? And like, I had a student years ago who used to say Chiku, so now I say Chiku. And when it's acetic acid, it's Chiku-H. I don't know. All right. It's not good when I've spazzed out and moved that. All right. Let's take care of business here. Our products have to be the same every single time. Those products need to be a salt, carbon dioxide, and water. And the salt's really the only part that may require some thought, because everything else is the same. So I'm going to leave room for our salt. And then I'm going to put CO2 and H2O. CO2 and H2O. CO2 and H2O. Oh yeah, CO2 and H2O. 2O. I'm doing this, I know it's semi-annoying when I set it up this way, and I just keep doing the same thing over and over, because I want to highlight the fact that it's the same thing over and over. All right? Now, when we're making our salt, we said it's got to be our metal cation with the anion from our acid, and I'm going to try and utilize highlighter technology. Metal carbonate, metal carbonate, metal carbonate, metal carbonate, metal, 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 right? So those are the things that I'm going to put right there. Okay, and then we've got our acids here, the hydrogen attached to some stuff, my chloride, right, my nitrate, my sulfate, and my acetate. And that's one that tends to throw people off. So now we've got that highlighted, and I need to put the pieces together over there. If you remember from the synthesis discussion, doesn't matter what your subscripts are on pieces of this over here, we're going to crisscross and reduce over there. So I need nickel with chlorine, and it's a nickel 1 plus, and I know that because there's a 1 out there. So let's make that compound happen. We've got nickel, that's a 1 plus, and I've got chlorine, that's a 1 minus. So I have nickel 1 chloride, right? In this one I have zinc nitrate. Zinc is a 2 plus, nitrate is a 1 minus, so it will take 2 of those. And let me make that 2 a little bit clearer. In this one, I've got iron. In this case, it's a 3 plus. So I've got Fe as a 3 plus. And I've got sulfate, which is a 2 minus. So I'll do my crisscrossing and reducing there. And then in the last one, it looks so scary, I know. But a strategy that I often recommend is, if it looks scary, just put your finger over it, right? Oh, whatever's under my finger is a 1 minus, and it's going to be attached to the sodium. So sodium is a 1 plus, and then this thing that I highlighted, Chku, is a 1 minus. This whole thing is a 1 minus. 1 minus and 1 plus cancel out and reduce. So there is the basic setup for those. I didn't budget my space well for balancing, but we'll see what we can do. We got 1, 2, 3, 4, 5. And we'll see how this goes. I'm going to remove my clip. We have nickel, carbon, oxygen, hydrogen, chlorine. I'm going to try and offset these. We have zinc, carbon, oxygen, hydrogen, and I'm going to super cheat here. If you have a polyatomic ion that appears on both sides, don't split it up. So like this is nitrate right here, and this is nitrate right here. And yes, I'm just cutting a corner. All right? We have iron. We have carbonate. We have carbon, oxygen, hydrogen, and sulfate. I can't keep that carbonate together because it's not on the other side. I have CO2 on the other side. Reactants and products. I realize this is a glorious mess at this point. We have sodium, and we have hydrogen that I already mentioned, but I'm going to separate it here. Hydrogen, and carbon, and oxygen, and Chku. And I'll scoot that up a little bit to make sure we've got it. All right. We've got 2 nickels, 1 carbon, 3 oxygens, 1 hydrogen, 1 chlorine, 1 nickel, 1 chlorine, 1 carbon, 3 oxygens, and 2 hydrogens. All right? All right, so as I look at this, nickel is no good, nickel 1, so I'm going to put a 2 there, and I have 2 of them now, right? And that also changed my chlorines, so now I have 2 of those. And the good news is, if I fix it over here with a 2, there is 2 and 2, and it's balanced. Whew, 1 down. On this one here, I've got 1 zinc, 1 carbon, 3 oxygens, 1 hydrogen, and 1 nitrate. All right. I could have split apart the nitrate, but I didn't have to, so I'm not going to. All right. If you can keep a polyatomic ion together on both sides, it's a little less work for balancing usually. All right. So I've got zinc, 1 of those on this side, carbon, 1 of those on this side, oxygen, 3 of those, hydrogen, 2 of those, and nitrate 2 of those. And so luckily we can put a 2 right there, and it's balanced. All right, 2 left, and we'll look at this one. I've got 2 irons, 3 carbons, 9 oxygens, 2 hydrogens, and 1 sulfate. And let's check that. 2 irons, 3 carbons, 9 oxygens, 2 hydrogens, and 1 sulfate. Right? Product side, 2 hydrogens, 3 sulfates, 1 carbon, 3 oxygens, and 2 hydrogens. All right, so let's work our way down. Good, not good. We'll toss in a 3 right there. That gives us 3 of those, and now we have 7 oxygens, right? And I warned you before that I often miss it, but 3 times 2 is 6. Oh yeah, there's one more, is 7. All right, hydrogens look good. Sulfates are messed up, so let's see what we can do. 6, 3 of those. 6. All right. So let's fix our sulfates. I'm going to put a 3 right here. That's going to give me 3 sulfates, but it gives me, in the process, 6 hydrogens. And I can fix that by saying, okay, I need to multiply this H2O by 3. That's 6 hydrogens, hooray. And now I have 6 and 3 is 9 oxygens, all right? Very, very important thing took place there, and that was I had my 6, and then I changed this and added them together, all right? And it worked out, 9, so that's spectacular. Last one, and here's why I saved that for last, and here's why I think it's kind of an interesting reaction to mention. When you talk to people and, you know, say, what's the first what's the first chemical reaction you remember seeing and thinking, oh, that's a chemical reaction taking place? Almost every single time they'll say the volcano reaction, where you mix vinegar and baking soda. Well, vinegar is acetic acid, CH2H, CH3COOH. It's like a 3% solution of that. And baking soda is sodium bicarbonate, or sodium hydrogen carbonate. So as we look at this one, this is baking soda and vinegar, and we get bubbles. All right, it's that volcano reaction. So I think it's kind of interesting that we look at it that way. All right, last one. Sodium, 1 hydrogen, 1 carbon, 1 oxygen, 3 CH2. Oops, we had 2 hydrogens. I'm glad I caught that. We have that hydrogen right there, and we have that hydrogen right there, and we have 1 CH2. All right. Product side, we've got 1 sodium, 1 CH2, 1 carbon, 3 oxygens, and 2 hydrogens, and it's balanced. And that's a very nice way to go out on our decomposition reactions. So we've got synthesis, regular decomposition, special decomposition, and we'll knock out the single replacement, double replacement, and combustion in other videos.